Hi and welcome back finally to the second part of Threadripper Direct Die. Many people asked for it and they were wondering where is the second video or the follow-up video regarding AMD Threadripper Direct Die. So far it didn't exist. I know it has been 6 months until we tried it last time, but I didn't really have time to do it until now. I always had it in the back of my head that we still have to do it and do a follow-up video on it, and that's what we're going to do today. I still have the same motherboard here. Everything is still exactly the same. The system was pretty much still assembled. Just to recap what we did last time, we had the 3960X AMD Threadripper CPU, which we successfully delivered by cutting around the glue with a sharp razor blade. Afterwards, removing the heat spreader using heat, put it in the oven at around 155 degrees Celsius, the indium is melting, then we could remove the lid of the CPU. We then put it back in the socket, but prior to that we had to remove some parts of the socket because, you know, the AMD Threadripper socket, the ILM, it is a little bit too high to fit a delivered CPU in there. Therefore we had to remove the top part of the ILM of the CPU socket, and then we were able to put the CPU back into the socket, put the CPU cooler back, which is a water-cooled Heat Killer 4. Still probably my favorite AMD Threadripper block. It's absolutely amazing build quality. Then unfortunately the CPU was behaving still the same as stock. Well, first of all, it didn't really work at all. We had a lot of contact issues, like it wouldn't boot, we were losing memory channels, which is usually a problem of the mounting pressure of the CPU. Taking into account that usually the ILM presses down the CPU quite hard into the socket, and then we don't have an ILM anymore. We only have a CPU block which is pressing the CPU in the socket. We definitely had some mounting issues, which then we were able to solve after mounting like 10 times and renewing the liquid metal. And then the performance was not great. The performance was pretty much identical to just stock, like with the IHS, nothing really changed. We were running Cinebench R20, 4.3 GHz across all cores, 1.4 volt, which is definitely quite a lot. And we hit about 85 degrees Celsius in Cinebench R20. That was the outcome from the last video. And in today's video, we're trying to fix what didn't work, or eventually we will find out that it just won't work at all. In general, I want to highlight that this is something I would definitely not recommend for you to try at home. That's something we will just do for this video. Even if it would give us like 5 to 10 degrees Celsius, I would absolutely not recommend to delete your AMD Threadripper CPU. You have to cut away parts from the socket, and I mean, you're losing warranty of like a 2000 euro CPU for 5 degrees Celsius. And for 5 degrees Celsius you don't get much. You cannot really clock much higher. Still, we will try if we can get it to work reliably and if we can improve the temperatures. Before we continue with this video, I have a question for you. Did you ever register to websites and then at the same time wonder or think, to how many of those have I been registered to and what are they actually doing with my data? Is there a way that I can find out how many websites store my data? And that's where we get to the sponsor of today's video, Mine. Mine can answer all those questions and is currently still free to use, so you can just go ahead and log in to Mine using your Microsoft or Google account. Click on See Your Footprint and you will see all websites which store your information. I was personally surprised how many results I had, especially considering that that's not even my main account. You can then further investigate which companies are holding financial data or identity data. If you find any websites you wouldn't want to store your information anymore, you can simply click on Reclaim Your Information and Mine will send out an automated email for you to execute your request. As I said before, it's completely free right now. They might introduce a subscription model in the future. To check it out, simply go to saymine.com or just check out the link in the description below. And that's how the block looked like underneath after removing the CPU. The liquid metal is not dry, it's still liquid, but it also kept the CPU sticking to the water block. Obviously the CPU is not held by an ILM anymore in the socket. Therefore it was stuck to the block, and yeah, that's not great. I mean, you can easily ruin your socket with that. First of all, let's remove this. In general, if you want to remove liquid metal, acetone is always great. We also made a dedicated thermal interface material cleaner from Thermogristy side. It's not available yet. Will be available soon though, but in the meanwhile you can just use normal acetone. Obviously liquid metal will always leave some kind of residues, but I think after 6 months that's totally fine. Yeah, looks good. Here we have the heat spreader, which we removed from the original CPU, and therefore, because we removed this metal part, CPU block is now sitting lower onto the CPU cores. Therefore, we have to know how thick this is. You can just use this micrometer and learn that it's about 3.1 millimeter in height. Now regarding mounting pressure, the thing is, as I said before, we removed the IHS, therefore the block is sitting 3 millimeters lower, and we have those screws which are used to mount the water block, and the screws, they have a limiting factor right here, therefore it doesn't matter how much the CPU block is sitting lower in the socket, you will always be limited by this part right here. The screws will eventually be in the same position as originally, and because it's sitting 3 millimeters lower, we're losing a lot of mounting pressure on the springs. And that's why I thought I will just go to Caseking and use some 3 millimeter acrylic parts to make some distancers, some acrylic washers, which I can put on the screws and therefore have eventually the same spring pressure as originally. That could improve the mounting pressure of the total CPU into the socket. And here we have the acrylic washer I was talking about, and this part simply goes just right into the mounting hole of the block, and then we're inserting the screw with the spring. Now in this state, the screw with the spring is sitting 3 millimeters higher than originally, but the distance to the socket is the same as originally, and therefore this should help with the mounting pressure issue. The second big issue was the contact that is only made towards the center. If we put the water block back on here, we only have contact on the core dies and also the big I/O die in the center. A lot of people asked, but they should have exactly the same die height. That should not be the issue. We will double check with the micrometer in a second, but that should not be the problem. The problem is most likely that right now, if we mount the water block, we only have contact in the center, but on the outside, where originally the IHS has contact, it would also apply pressure to the edge, which is not happening anymore. Therefore, we will just take some 1 millimeter thermal pad, because the dies should have around 0.8 to 0.9 millimeter height. Put them on here, here, and maybe like the side. They are compressible, and that could help with the issue of having bad contact in the socket and then losing memory channels. This could maybe solve this problem. First of all, we have to check the PCB height, doing it in a corner where we don't have any glue. And it's pretty much 2 millimeters. It's 2.07 millimeter PCB height. And now clamped to one of the CCDs on the side, you can see measuring 2.9 millimeter. Therefore, yeah, it's about 0.8 millimeter die height for one of the CCDs on the side. And just to confirm, the I/O die now measured in the center, it's the same 2.9 millimeter. Therefore, all the chips have the same die height. That is not causing our issues. By the way, I also found something which is also interesting, I think. It's a vapor chamber, which I found at QuickCool. That's a German shop where you can just purchase heat pipes and all kind of heat pipe based cooling solutions. And they also had this vapor chamber in their online shop. And surprisingly, it's pretty much the same size as just the CPU cores, if you just compare it, and height-wise, it's exactly the same as the stock AMD Threadripper IHS. So in case if it doesn't work out with like mounting pressure and stuff, that's something else we can try in the end. Maybe because, I mean, spreading the heat should be better than just having this massive piece of solid copper, which is the stock AMD heat spreader. Maybe this will improve things, but first of all, we will cut a thermal pad into shapes and just cover those parts on the corner. I just noticed that I also have to remove the glue, which is still left on the CPU, and then let's just see if we can do the normal direct die. Fun fact, it's quite easy to remove the glue with a defect 9900K. The PCB is quite sharp, and that's helpful. Here we have the thermal pads applied, and now I will have to reapply the liquid metal to IO die and also the other CCDs. And then hopefully it will work. And here we have our board. You will probably remember from last time, that's the area where we cut off the original ILM, which is pushing down the CPU. And CPU back into the socket. Already reapplied liquid metal to the block. Now carefully putting this thing back onto the CPU. Now putting all the distance washers, the acrylic ones, onto the block. Come on. Ready for the test. I didn't put in the water cooling gear so far, simply because if there's any issue, it's easier to remount the block when it's not filled. Memory is in place and GPU is in place for basic PCIe test and also memory test, and that should be visible on the debug LED. Cycling through all the memory codes, therefore it's a good sign. I mean, no 00, no like 55 and stuff. Looking good so far. Display signal, we have all memory channels. I'm not going to stretch this because cooling is going to be bad, putting on water cooling. Okay, kind of the big moment. So far everything is running fine. We have all the memory channels detected, VGAs detected without any issues. Therefore, it's a mounting improvement over last time. The question will be the temperature. Right now everything is running stock. I will just run Cinebench R20 and then let's see how the temperatures look like. We have at least one improvement over last time, and that's hardware info. The newer version can detect individual CCD temperatures, therefore we have 4 CCDs right here. And what's a little bit weird, we have 40, 50, 40, 60 degrees Celsius max for the 4 CCDs, 64 on CPU die, and then the CPU temperature is reading peak 75. I mean, where is this temperature coming from? I don't understand it. I don't get it so far. Let's see Cinebench. That was not a good sign. Second attempt, this time with R15, a little bit lighter load, no AVX. However, the temperatures, they're not looking great. This turns out to be much more difficult than I initially thought. I tried it 3-4 more times and it's always the same behavior, instant crash or instant shutdown, therefore it's like a thermal protection. I also tried to loosen and tighten the screws again, which didn't help. Maybe just let's take out the CPU back out of the socket and investigate the mounting pressure, mounting contact between the block and the CPU. First look on the CPU itself, looks good. I mean, you can see some lines right here or in the corner. I'm not sure if you can see it, but there we had definitely contact with the CPU block and the thermal pads. I mean, mounting pressure wise, we had no issues. Like memory detection, everything was great. Also, liquid metal was fine. And on the block itself, yeah, we have definitely marks. We can see all the small CCDs, all the dies, IO die, everything is here. Therefore, like, yeah, contact should not have been the problem. Let's try it one last time. I removed a thermal pad from here and here. Maybe it was taking off too much pressure from the center. Again, one day later, making progress, not so much about the temperatures. Those temperatures are still not great. I think they will not improve much when it comes about direct die, but I'm trying to detect which... In case you're wondering about the background noise, I'm not even sure if you could hear it, but we got this new toy for Chic and she absolutely loves it. I think she's been playing with it for like 30 minutes already. I'm trying to detect which die is exactly at which position when it comes to hardware info, because hardware info is listing die 1357, but we don't know at which position is which die. And especially with direct die, if I mount a cooler and one has bad temperatures, I don't know which one needs reapplication of liquid metal, and therefore I'm trying to figure out which position is which die. That's the current state. I'm pretty sure about die 1 because once I had really bad temperatures and then the reapplication had improved drastically by like 20 degrees Celsius on that single die. Therefore, I'm sure this is die 1. On the one in the back, it could either be 3 or 5. Not sure because I reapplied liquid metal here and it improved on 3 and 5. Therefore, not entirely sure. Right now, I think we will just remove the liquid metal from this one and then see if the temperatures get worse on die maybe like 5 or 7. Therefore, we should maybe find out more. That's the result. One has no liquid metal, the other one have typical liquid metal application. Let's remount and see which one has bad temperatures. By the way, I have still liquid metal applied to the block because if there would be no liquid metal at all, like no contact to the block, it would certainly just die because the mass of the die itself is so low, it's like 0.3 grams. And that cannot compensate anything. If you would put a sudden load onto the die, not even the thermal protection could probably save it. Therefore, there is a certain risk to what we're doing, and yeah, I wouldn't recommend to do that at home. I'm also wondering if I could do it differently, like with disabling dies in BIOS, but yeah, let me think about that. Perfect, we got what we were looking for. If I just run Cinebench R15, keep your eye on CCD5. You can see this one is significantly warmer than the rest. Therefore, the one which we just used for not applying liquid metal is definitely CCD5. I mean, the others were like 50, 40, 50 degrees Celsius. Therefore, we know this one is die number 5. And because previously I was not sure if this was number 3 or 5, we know that this one is 7. And this one should be number 3. That should help significantly in debugging with direct die. Now I will try to improve the mount, maybe mount 10 more times and see how we can improve the temperatures. Okay, after, I don't know, at least 10 more mounts, it's absolutely impossible to get the perfect mount. Every single time it's either like die 1 and then it's die 5, but just to get like a very good mount, just look at the temperatures. CCD1 is now shooting up to over 100 degrees Celsius. It's absolutely on the edge. Give it 1 degree more and it would just thermally shut down. I'm definitely a patient person, but I also have my limits, and after literally mounting the block 50 times in 24 hours, at a certain point you just have to sometimes agree that things don't work. And that's probably the case when it comes to direct die in this configuration. Last thing which we will try for fun is the vapor chamber. Let's put it on to the CPU and between the block, see if this improves things or makes it even worse. Pretty sure you've seen such vapor chambers before. Nothing spectacular. They've been used many times in GPU coolers. This should be the side that should make contact with the dies directly. Therefore, cleaning is first, applying liquid metal to the whole surface, putting it on there, and then also once it's mounted, put some liquid metal on the backside, and then sandwich this between CPU and water block. The cool thing is we don't need the washers anymore because it's back to original mounting height with the same height of the vapor chamber as the original IHS. Moment of truth, I already ran it in a German video, but you can already see the peak temperatures are interesting. This is not even bad. I mean, this is better than what we had with the normal direct die. Cores are pretty much equal, that's also interesting. Back to original testing, which we did in the first video, 4.3 GHz, 1.4 volt across all cores. Stock was running certainly fine on the temperatures, and now just with OC, see if things are getting worse, or let's see where we're at. Yeah. That was very, very close to shutdown. Very, very close. Alright, I think it's time to just cancel this project in total. Threadripper direct die just does not work. It makes no sense whatsoever. It has a beautiful IHS on their stock. It's soldered. you just shouldn't touch it. And I think that's exactly how we're going to end the video. Vapor chamber was interesting. I personally never tried this before, but also the heat output is too high of the Threadripper for this vapor chamber. I think this one was capable of about 150 watt, the vapor chamber, and I couldn't find bigger ones. I mean, dimensionally wise, I could find bigger ones, but not for the heat output or the heat transfer. I think this one was capable of around 150 watt, and that's certainly too low for an AMD Threadripper CPU. Anyway, I hope you had some fun and we could finally cancel or finish the AMD Threadripper Direct Die project. Thanks for tuning in. See you next time. Bye.